Hello, everyone. Today in this presentation, I will be presenting the power of true believers in topics in mathematics. So here's the table of contents. First is dynamical systems, a little background. Then we're going to more specific with 1D bifurcation. Then even further with 2D bifurcation, and then the example I have planned. So, what are dynamical systems? A dynamical system is a system whose state evolves with time. So, there's two types, which are differential equations, which most people are more familiar with, and integrated maps. So, a differential equation describes the evolution of systems in a continuous time, while an integrated map arises mainly in problems where time is discrete. So, to working with differential equations and with dynamical systems, we first need to find the fixed points and stability. So, in a one dimensional system, is when x prime is equal to f of x, which is a function. So, the fixed points x star are defined when f of x star is equal to 0. So, you can see on the graph on the right. Um, what the points that are equal to 0, they cross with the x-axis. And when it's shaded in dark, that means it's a stable node, while when it's not shaded or in white, it's an unstable node. So you can see the arrows, they are pointing towards the stable node and away from the unstable node. So now we're going to 1D bifurcation. So bifurcations, there's mainly two categories, which are in one-dimensional systems and two-dimensional systems. But either way, they are dependent on parameters, which can be labeled as R, A, mu, any letter you desire. So it is the qualitative structure of flow that can change when parameters are varied. So in general, the fixed points, as described earlier, can be created, destroyed, or have a change in stability. So go from stable to unstable or unstable to stable. So, what is bifurcation exactly? It is a qualitative change that occurs when a modification is made to parameter values or bifurcation parameters of a dynamical system. Why are these bifurcations important? Well, bifurcations can provide models of transition and instability as some control parameter is varied. So in the example I have below, there's applied load on a piece of wood, and then you can see how it buckles under load, and when you release it, it is nice and straight when it's unloaded. So we can use bifurcation in that example to figure out the curvature or the u parameter. So for 1D bifurcations, there's several different types. The first type is the solid node bifurcation, in which the fixed points move toward each other, then collide, and then they are destroyed. And their first order system is described as r plus x squared, where r is a parameter. So as said earlier, bifurcations are dependent on time, so that's why the first order system is labeled as dx over dt, which t is referring to time. So in order to solve for the fixed points and their stability, we must set that equation equal to 0. So I have on the left dx over dt equals r plus s squared. We make that equal to 0. We essentially uh, solve for r. That's supposed to have a negative x squared, my bad. And then we have the fixed points as negative r to square root, and again, negative r to square root. And we know that the bifurcation point is at 0. So then we're going to go into transcritical bifurcation, is when the fixed points change stability. The normal form is rx minus x squared. So you can see, let's say at x equals to 0, that's one of the fixed points in the graph below. You can see how it's stable, so the arrows are pointing towards it, and the dot is at x equal to 0 is filled in. And then as r becomes 0, so it kind of shifts, you see that it's kind of half shaded, half not, which means it's semi-stable. So you can see how the arrows are kind of in a weird direction because they're semi-stable. And then as r is positive or greater than 0, you see at x equal to 0 that it becomes unstable. So now the arrows are pointing away from it. So you can see that there is a change of stability. So then we have the other example, which are Pittsburgh bifurcation. There's two types, supercritical and subcritical. They're defined as when the fixed points appear and disappear in symmetrical pairs. So the graphs you can see as r is less than 0, at, at x equal to 0, it's stable, and then r equal to 0 is still stable. But then when r becomes positive, there's a great change where now at 0, it's unstable, but you can see that they're at the endpoints that it's going to be stable. So this is what they mean in appear and disappear in pairs. So they're first stable, appearing together, um, and then they become unstable. So now we're going to go into 2D bifurcations. So as discussed earlier, even in a 2D system, bifurcations are dependent on a change of parameters. Instead of a 1D system with one function, now we're going to have two, so like f of x and g of x. Actually, f of xy and g of xy, excuse me. Another important definition are for nullclines, and nullclines is the intersection of the fixed points. So now we're going to go with what we've seen earlier. So for a saddle node bifurcation, the fixed points move toward each other, collide, and then are destroyed. So now the system looks a little bit different. Instead of r, we're going to use the parameter of a. So now x dot is equal to a minus x squared, and then y dot is supposed to be negative y. So it's still the same situation when you have to find the fixed points. You get in this case now it's like you have x star and y star instead of just x star. So it's kind of a similar one as we saw earlier, is negative square root of a and 0, and now it's a square root the square root of a comma 0 for the 2 points. So again, you can see that the fixed points, they move together, they collide, there's a bifurcation as a equals 0, and then as a becomes greater, let me see if I can move this. Yes, you can see they're destroyed. Actually, no, it's the other way. As a becomes greater, the fixed points are moving together, moving closer to each other, a equals 0, there's a bifurcation. A is less than 0, then they're destroyed as you don't see anything. So now we're going to go into 2D bifurcation. Um, still, now there's the transcritical bifurcation. Again, the fixed points change their stability. As I explained earlier, in the center there, you can see at x equal to 0, you can see how it's stable, and then as a approaches 0, or a equals 0, it becomes semi-stable, and then a is greater than 0, it becomes unstable. So it's the same approach, it's just that now we're working with second order instead of first order. So now we go into pitchfork bifurcation. Again, it's the supercritical pitchfork and the subcritical pitchfork. They still, the fixed points change their stability. So earlier we saw that, let's see. Yeah. So they arrive in pairs and then they disappear or they change. So they arrive in pairs and then they change. So this again with subcritical. So you can see at the right last two, they're in pairs with unstable nodes. So now we're going to go into the example, the power of true believers and their relation to bifurcation. So here is the part of the question statement. Sometimes a small band of unwavering advocates can win an entire population in this point of view. So consider the following stylized model as these situations as studied by Marvel. So I just wanted to make sense and use different little figures. I decided to go with the Among Us theme, so that's why they're all there. So the population is divided into four overlapping groups. There's group A, group B, and then there's group two versions of group AB. You'll see in a minute why it's labeled like that. So initially, a small group of true believers hold opinion A. In this case, opinion A is that cannabis should be legal. I wanted to make it a more modern approach rather than women deserve the right to vote, since they all do. Um, so nothing that anyone says or does can change their minds. So then there's another group of people who currently agrees with them, but they're uncommitted to A. So if someone argues with them, like in group B, the uncommitted A believer can become a B as they see both merits of the situation, both positions of the situation. So you see on the left, cannabis should be legal with the A group, and then blue is that cannabis should be illegal. But then pink, after talking with blue, sees the harm of cannabis. So they're undecided, or not undecided. You just see both positions, and that's why they're in the middle. So, likewise, with B believers can instantly turn into A B subpopulation when confronted with an argument for A. So, similarly, on the blue side, cannabis should be illegal, and on the red side, cannabis should be legal. But once a blue member talk to a red member or a red person, they become green and they're still in the AB subpopulation as they see the benefits of cannabis after talking to red. So the green and pink people are in the same group. I just differentiated depending on where their starting point was, whether it was red or blue. So now we're going to go into the meat of the problem. Assuming the members of the four groups mix with each other at random, the governing equations for the dynamics are as follows. They're a bit complicated. So where NAB is equal to 1 minus P plus NA minus NB. P is the unchanging fraction of true believers in the population. NA is the fractions of the A subpopulation, and that's the same with B subpopulation and the AB subpopulation. So now the first part is to interpret and justify the form of the various terms in the governing equation. So essentially, as we've talked about before in the bifurcation topic, that it's dependent on parameters and also dependent on time. So in this case, n dot A is supposed to be the rate of change of the incoming or of the population of A. So you can see that in the first part, they're gaining members, which are dependent on P, and P was the unchanging fraction of true believers in the population. So NA is always going to be sticking with P. And then but that's also dependent on the subpopulation AB because there's going to be some members who choose to be A after having an argument. But then you can see that there's a negative portion of it, and those are the people that are leaving group A and they are either turning into they're probably turning into group B, so that's why there's a negative portion. And it's the same with n dot B is the rate of change of the population of sub B. So the positive part is the part where they're gaining members, and the negative part is when they're losing members to subpopulation A. So now we're in part B. Assume that initially everyone believes in B except for the true believers in A. And then we must numerically integrate the system until it reaches equilibrium. Show that there's a critical fraction of true believers, PC, so that P less than PC, most people still accept B, whereas P is greater than PC, everyone comes around to A. So now the graph below is what it should look like after being numerically integrated. And you can see how it's kind of divided into like three parts. The the pink or the red part on top, the blue on the bottom, and then the questionable green. So when the green part is where PC should be, We don't know exactly where it is, but it should lie between when p is equal to 0.1 and p is equal to 0.2. We don't know exactly that number yet, but we know anything below PC, people are going to be accepted as B, and if they're above that critical part, they're going to be accepted, they're going to be coming around to group A. So I kind of labeled it as the colors of the group members earlier. So now we must show that PC, which is the critical part, is equal to 0.13. So that means that 13% of the population needs to be unwavering advocates to get everyone else to agree with them eventually. So what I did is that we made n dot b is equal to 0. So that was the original problem, n dot b is equal to 0. And then after doing some basic algebra, we have that NB is equal to 0 and NB is equal to 1 minus 2P minus 2NA. So to get there, we had to substitute NAB into its version of NA and NB as is stated in the middle over there. So with NB, we're gonna need it to find N dot A. So again, I have N dot A written. And there's going to be kind of two cases with this. Now that we know that NB is equal to 0, we can find the first NA. So again, after plugging in for NAB and plugging in that NB is equal to 0, you get NA is equal to 1 minus P. So instead of having P plus A is equal to 0, that wouldn't really work out because the NA, which is supposed to represent the population of A, should not be equal to a negative number, so that wouldn't work out. That's why we have NA is equal to 1 minus P. And then again, with the second case, NB is equal to 1 minus 2P minus 2NA. So again, we solve it. It was kind of a long process, but then we got P squared plus 4P NA plus 3NA squared minus NA is equal to 0. So in order to solve for NA, we must use the quadratic equation. So instead of writing it all out, I decided to simplify it. So in this case, after I guess reformulating it, you have A is equal to 3, B is equal to 4P minus 1, and C is equal to P squared. So after filling that out in the equation, you get NA is equal to 1 plus or minus the square root of 3 over 2, which is equal to around 0.13. So solving that part was very important. So now the last part is what type of bifurcation occurs at PC, and it is the saddle node bifurcation. So it kind of relates to the graph we saw earlier. The definition of saddle node, let's go back. Let's see. The fixed point move toward each other, collide, and then destroy it. So based on what we've learned, we can see that at PC, since that was the most critical section, um, then at that point it is the saddle node. So yes, that is the end of my presentation. If there are any questions or any comments, please free please feel free please please let me know. Thank you.